Good morning, everybody. Free Coke for whoever guesses my outfit, what my Halloween costume is, by the end of the class. Did everyone see the announcement about the exam wrapper? Yeah. So I had a number of suggestions from students, talked to a lot of different people, try to figure out the best way that was the most fair. And that's the best I was able to come up with. It is half of the credit for the individual questions. One thing I will be really, really specific about, you have to follow directions, and when I read it, I have to be convinced that you understand how to do that problem. If it's a problem you just didn't have enough time on, your explanation is going to be very different than if it's one that you actually completely put something that didn't make sense. Okay, so I need you to think very carefully about what your answer was, whether that made sense, and then give me insight. I don't have time to sit down and interview every single person on every topic, so please make sure that it's very clear to me that you now understand the topic. Maybe you did at the time of the exam. Does that make sense? On the exam 1 wrapper, I think only out of the people who submitted it, people probably got about 70% of the points back that they could have because the explanation wasn't clear or it didn't fill my qualifications of you understanding, show me you understood why your answer was wrong and why the other answer was right. You have a fan inside there?
Do you want me to turn it off?
No, you're fine. All right, any questions about the exam wrapper? What does it do? Do it at the beginning of class 1 week from right now. You have a whole week, and if you, I would highly recommend if you want to study, to work with other people, see how they did it. We'll do the same thing. Come up, put your name on here afterwards if you want to pair up with other people in the class and work with them to make sure you maximize the amount of credit you can earn back, okay? Angel?
We do this after, does that mean we can't have our final?
Correct. So this is, once again, in place of the final exam. One of the other ideas I was thinking about was to give less credit back and then also allow it on the final, but I think logistically that was too confusing. So if you do the exam wrapper, it is in place of point recapture on the final exam. I would imagine that if you do the exam wrapper fully, you're going to maximize the points you can get back as opposed to waiting for the final exam, but that's up to you. So if you already have a relatively high score and you think you'll crush the final, then wait and do it on the final. It's in, what, 5 weeks? If you want to make sure your grade right now reflects what you think you're capable of, then do it. I have office hours Monday, Tuesday, Friday. So I have them this upcoming Friday, next Monday, and Tuesday. Yeah.
Can we still do point recapture for exam number 2 even if we have done wrappers?
Yeah, so we didn't do exam 2 as a wrapper. There's no wrapper. It will only be point recapture on the final exam. So, and if you did not do the exam wrapper in exam 1, if you chose not to do that, you will have point recapture from the final for exam 1 topics as well. All right, let's go ahead and get into it then. Go ahead and tell me what the oxidation number is for carbon in methane. Talk to your neighbor. If you're not sure how to do this.
I'm sorry, I didn't but it also
Where is it? I don't understand. Terrible idea.
Ouch.
All right, I hear a lot of side conversations. So let's talk about this. We have a table down below on your worksheet that compares formal charge and oxidation number. So what I'm going to have you do, go ahead and draw the Lewis structure really quickly for methane. Draw that out on your paper.
Oh, I don't want to.
Do it. Nice and big.
Oh my.
By the way, if you did not pick one up because you came in earlier, missed it, the handouts in the back, the worksheet, and the exam wrapper. I need to have that stapled and put to the front of your exam. And please follow the instructions. There's some instructions on there. If you don't complete that, I can't give you credit for the exam wrapper. All right, so Anthony drew our methane molecule here. If we're doing formal charges, I'm sure it's everybody if it's you. Flash flood warning?
I didn't hit it, so.
Okay, we're about to all go off. So if we're doing formal charges, how do we count each of these 2 electrons? Do we count them for the carbon? Do we count them for the hydrogen for formal charge? Everything's going off. One of them for each, right? We say, well, they're bonded, so they count equally for each atom. That's not true for oxidation number. So what we're going to be talking about for oxidation number, we are counting the same electrons. Which electrons are we counting in a molecule? When we're talking about a Lewis structure, all valence electrons. So no matter what we do, whether we're doing formal charge or oxidation number, we're counting all valence electrons. That's that top line on your table, in case you're wondering. But we're going to count them differently. So in the case of formal charge, we split them equally. But in the case of oxidation number, they are counted only towards the more electronegative atom. So let's take a look at these electrons shared down here. What's more electronegative, carbon or hydrogen? They're really close, but they're not the same. So we're going to say that carbon gets to count these electrons,
Gets to steal all of them.
these ones, and these. So carbon gets to count all 8 electrons. So how many electrons, valence electrons, is carbon supposed to have?
4.
Supposed to have 4. So then what's the oxidation number if it gets to count all 8? No yelling out. Let's do fingers. Is it positive or negative 4? I like Joey. Negative 4. So it has 8. It's supposed to have 4. So it has 4 extra electrons. Remember, electrons are negatively charged. So the oxidation number of that central carbon is -4.
Another question. So, like, for the homework, they showed us how to do it like a chart.
Yeah, there's a memorization way which I wanted you guys to be exposed to, which is why I give you the homework. But if you want to save up some brain space for thinking and not cramming stuff in your head, let's think about it this way. It's going to make your life way easier. So if that's the case, if carbon has an oxidation number of -4, talk to your neighbor, what is the oxidation number for each of the hydrogens? So I hear a lot of mumbles that are the same thing. So it should have 1 valence electron. It has 0, so that means it's missing 1 electron. If it's missing an electron, it's supposed to have, what's the oxidation number? +1. All right, so then if we zoom out, it's probably going to take way too long. If we look at oxidation numbers, we have +1, +1, +1, +1, -4. What do you notice about the sum of all the oxidation numbers?
They're 0.
Okay, so it's 0 for this particular molecule. Why is that okay for this molecule? How do we know that that's what it's supposed to be? Eric?
The molecule doesn't have any charge.
Great. The formal charge of the molecule is 0, which means the sum of all the individual formal charges has to equal 0. But also the sum of all the oxidation numbers has to equal 0. Both of those are true, because we're only counting the valence electrons. No matter what, we're only going to have a total of 8 electrons. The question is, where do we count them? And if we end up with an oxidation number or formal charge that's not 0, it means we either didn't have enough electrons or we counted too many electrons. So, if we go back now and look here, can you guys fill in this table? Go ahead and fill it in as best you can, ideally with a pencil, and then we'll talk through each of these 3 categories. So the question is, how do we count lone pairs? How do we count bonding electrons? Okay, so let's start at the top. Which electrons are we looking at for formal charge? Valence electrons. What about for oxidation number? I'm not sure how this is animated. Sweet. All right. So then when an element like oxygen has lone pairs, who do we count that towards? We count it towards that element, right? What about for oxidation number? But they're only on one element.
So they only have to count towards that atom again.
Same thing. So the only difference between counting oxidation number and formal charge is the bonding electrons. So how would you describe, can I get a hand raised? How do you describe how we count the bonding electrons in formal charge versus oxidation number? Someone volunteered. We've heard from you a couple times already, Ruby.
In oxidation, it's counted
A little bit louder.
In oxidation, it's counted towards the more electronegative atom.
And then in formal charge?
And formal charge is shared between the two.
Great. So a lot of students get in this mindset, I got to memorize this table of oxidation numbers, and then you don't remember necessarily all the rules for what's what. This is the only difference right here. For oxidation number, it goes to the more electronegative, counts towards. But I want you to be careful. Remember for that last molecule, the way that we counted electrons, does that mean that the hydrogens have a +1 formal charge? Don't confuse formal charge and oxidation number. Just because we have a +1 for one of those doesn't mean that both of them are +1. Right? So you have to go through and do the different rules for counting each one of them. Why is hydrogen in that list that you're supposed to memorize? Why is it almost always +1? What's that?
Only one proton.
True, but why is the oxidation number almost always +1?
Because it's the least electronegative.
It's one of the least electronegative elements. So whenever it comes in a battle, it's always sharing 2 electrons, it's usually going to lose the battle, and it's going to have 1 less electron than its valence. Why does oxygen almost always have a -2?
Because it likes to eat up.
Raise hands. Raise hands. I want everyone thinking through this. So think about the numbers you had to memorize last night, or you used in order to answer the questions on your pre-class worksheet. Why is oxygen usually -2? Why is it that the halogens are usually a -1? Think about that. Talk to your neighbors for a second. Where do those trends come from? All right, Aaron, did you want to answer the question? Yeah, so most of the time, the more electronegative elements, the halogens, are going to have more electronegativity than what they're bonded to. So that means they're going to pull 1 bonded electron towards themselves, 1 more than they had, so they have -1. What about oxygen? Why is that a -2 then? Okay, and we just want to be a little bit careful when we make that statement. It has a very strong pulling power, it's very electronegative. That doesn't mean that the formal charge is -2, right? So we need to say that the way that we count in 2 different ways. One shows us that the oxidation number will count those towards itself, where formal charge won't. So if we look at every time we've seen an oxygen, you guys have drawn a lot of Lewis structures by now. So pretty much every time we see an oxygen, it's either going to have a double bond or 2 single bonds. So that means that it's going to get 2 extra electrons counted towards itself. What's the exception? When does oxygen not have a -2 oxidation number? Kayla?
With peroxides.
What does that mean? Reading stuff's great. We got to know what it means too. Take a guess. Picture it. When is something not going to be more electronegative than the thing next to it? Okay, so when it's bonded to fluorine, it will not win that battle. Our book honestly uses that as just to help you know the rules, but almost guarantee you will never see an oxygen-fluorine bond in real world. It's just something the book likes to show. So what's another time?
If it's bonded with a atom of the same element, it's going to be equal electronegativity.
Really, really important point. Is this only true for oxygen? When any element is bonded to itself and itself only, it will have an oxidation number of 0. Because it will not win the battle, they will share them equally. Alright. So then, what I want you to be able to do today is obviously identify the oxidation number, but then we're going to be talking about locating changes in oxidation number from reactants to products. And then in doing that, we can determine how many electrons are transferred every time a reaction occurs. So if we have simpler oxidation reactions, a lot of times we'll just see an ion. So we see iron 3+. What's the oxidation number?
3+.
Plus 3. What's the formal charge? So before today, you would have said, well, that's the formal charge, right? That iron has 3 less electrons than its full neutral element. In this case, it doesn't matter how you count bonding electrons. There's no bonds. So what can we say about the oxidation number and the formal charge for an ion like this? They're the same. They're equal to each other. So in this case, the oxidation number is +3. Formal charge is +3. Once again, we're thinking about all the valence electrons, right? And we're determining, well, do they count differently because of bonds? If there's no bonds, we don't go down that road. All right, so let's take a look at these guys. I don't really like these questions. Do I have these in the worksheet? I do. Let's skip over those, and let's instead look at this problem. What problem number is this? Problem number 7. All right, so go ahead and try to assign oxidation number to every element in the reactants and the products. All right, so let's talk through this. Very nice weather outside today. So if we have, I saw 50-50 mix, I'd say, for the oxidation number for aluminum. Half the class said +3, half the class said 0. I want you to talk to your neighbor and try to determine which of those two is the correct answer. All right. Go ahead and click in what you think the oxidation number for aluminum is.
In the reaction?
In the reactants. Thank you for clarifying. On the left side of this reaction, what is the oxidation number of Al? Closing out. All right, so our majority answer is 0. Why is it 0? Sorry, I'm going to close that. Can I have a hand raised? New voices? Crush?
Because it's a solid.
Okay. And
it's not necessarily bonded to anything else.
Okay, so one is not bonded to anything else. It is a solid, and typically when we see an element as a solid, that is a rule. Josh?
It's not ion.
Great. That's the most important thing, which most solids are not ions, so it falls in track with that. But if we see this, there's no +3. There's no formal charge. We know that it has all of the electrons and it needs to be neutral. So that means that we can't say that that has more or less oxidation number because it's not sharing with anything else. Is that true over here?
No.
Okay. So go ahead and click in what the oxidation number is for the aluminum in the products. And remember, the plus and minus is very important to keep track of.
I am finding this soon. I am not winning.
You do per what each of them is. So you're right. Okay. There's two ways to answer this question, to get to the answer to this question. Can I hear from two different people how you approach this? Maybe there's more than two, but there's at least two that I can think of. Our class is really quiet. If we only hear from 3 people today, this is going to be a very boring class. Christina?
I don't know exactly how to do it. I know there's a way you do it using algebra. We can do fill in O with -2, I believe, and you can times it, I think, by 12.
Okay, so if you do remember that oxygen is almost always -2, then that helps get us on the right track. But we kind of get stuck a little bit there. Kayla, you want to add to that?
I do it how the book does it, trying to solve an equation almost for x.
Okay.
Yeah, so it'd be so I did 12 times -2. Then for sulfur, I did 6 times -3. And then
Why did you do sulfur as -3? All right, so let's pause, let's back out. I want to take a look. The reason I asked you to memorize polyatomic ions is not because I'm mean. Because when you look at a molecule like this, you need to immediately know where are the polyatomic ions, what's their formal charge, and then we can back it out from there. Okay? So this polyatomic ion is?
Sulfate.
Sulfate, the charge is? So SO4, 2-. What does that tell us about all the oxidation numbers? Joey? The sum of all of them is -2. All right, and we're pretty much going to assume oxygen is almost always -2. So then what does that mean sulfur is? So we have 4 -2s plus question mark, which is our sulfur, gives us -2. So then our sulfur has to be what oxidation number? Plus or minus? Okay, so recognizing the polyatomic ion saves us a lot of heartache. I don't know if it'd be possible otherwise. It might be possible. In this case, it's possible. What's the other way we could? Well, from there, what do we say the aluminum's oxidation number is? Joey, how are you getting 3? And it's really important we say plus or minus when we're doing this because it can be assumed it's one or the other. So we always say it's an oxidation number of plus 3. Did anyone else figure out the oxidation number for aluminum a different way? Jackson?
Okay, so look at aluminum on the periodic table. It's in group 3A, or 13, if you follow that one. But that basically means that it almost always has an oxidation number of positive 3.
If it's not a solid, that is an absolutely true statement. It always, if it's an ion, aluminum will always have a plus 3 formal charge, which means it always has a plus 3 oxidation number. The 3 that we need to memorize, I don't know if we went through this before, aluminum is always a plus 3, zinc is always a plus 2, silver is always a plus 1, if we find them as ions. They're not always ions. They can be a solid as well, right? Aluminum is not an ion here, but if we do find it as ion, it's always going to be plus 3. So those are the two ways. The first way was deductively. We know what the overall formal charge of sulfate is. We can figure out what the formal charge of the aluminums are. Because the net ionic equation, let me go ahead and erase this. If we were to write the net ionic equation on the right side,
Wait, aluminum, solid aluminum is aqueous?
we're getting. So we're looking at the right side of this equation. So because it says aqueous, we know that this is going to break up into an ion. That means it's not bonded to anything. That means that we can figure out what the formal charge is. So maybe if we're looking at this, it's not as intuitive that this is one of the ones we talked about. If it's an ion, if it's by itself, then the formal charge is the oxidation number. So that's kind of what I want us looking at, is that this, by saying it's aqueous, we know that this is going to be an aqueous ion. The question is, what's the formal charge of that ion? Because it's by itself, that's also the oxidation number. Questions? Can you do the rest? Go ahead and make sure you have the rest of the oxidation numbers written out. So the way that I'd like to see this is you can say 0, you can say for aluminum it's plus 3, sulfur, what do we say, plus 6, oxygen is minus 2. So we'll go through and say every single atom what the oxidation number is. I know there's 2 of them. That's relevant, but right now just identify the oxidation number for each element.
So you want to give each element not like half time?
Correct. So in the first, in sulfuric acid, you're going to say for hydrogen, sulfur, and oxygen. Couple more seconds. I'm going to cold call this, so make sure to check with your neighbor. Make sure you know an answer you can give and justify it. All right, can I hear from Dawn? The hydrogen and sulfuric acid. Why did you say plus 1? Great, so you went about it 2 different ways. I love it. So one, hydrogen is almost always plus 1, right? That's one of the rules. Because it's less electronegative than everything else, it usually loses that competition for the bonds. And then you said also, we know that this is sulfate. You recognize that right away. And you said sulfate's always a minus 2 formal charge, which means that some of the oxidation numbers is minus 2. That means that this has to be 2 plus 1s. All right, Markeith, what is sulfur's oxidation number in sulfuric acid? Positive or negative? How'd you figure that out? We can't do it from the periodic table. It's much more difficult to do from the periodic table because it depends on how many oxygens are attached. So we got to be a little bit careful there, and that's why going through the steps we did earlier is good. What about the oxygen, Tyler? Okay, And what you're going to notice, was there any change in sulfate from the left to the right side of the equation?
No.
All right, so that's going to tell us something really important, that probably was a spectator and that did not participate in the reaction. So that means that we can start focusing on other things. So whenever we're looking at redox reactions, we always look for something that doesn't change from the left to the right. That means we can kind of leave that aside, especially if it's aqueous, because that means we're going to have sulfate and sulfate. So sulfates are spectator ion in this case. All right, last one. Can I hear from Natalie? What's the oxidation number of hydrogen in the products? How do you determine 0? Can you say that again? I'm sorry, I couldn't hear.
I looked at hydrogen the same way that I looked at aluminum, that it's not bonded to anything else, so you can't use it for one charge plus 3.
So we got to be a little bit careful. Josh, you want to add to that?
If it's a gas, isn't it automatically going to be bonded to itself, H2?
So it is bonded to something, but what's it bonded to? Itself. That changes the story. So aluminum literally is aluminum. Each atom kind of fights for itself and is by itself. Okay, there's a lot of them together because metals are big groups of aluminum atoms with 0 formal charge. Here, the hydrogen is bonded to another hydrogen. That means that there's 2 electrons that we have to count. Neither one is going to win the battle for those electrons. None of them are more electronegative than the other, so each one gets to count 1 electron. Should have 1 electron. It does have 1 electron. Oxidation number is 0.
And also because hydrogen is one of those, I forgot what it is, where they bond to themselves.
Diatomic molecule.
Yeah, that word.
Yep. So H2 bonded to itself. What are some other ones that are always bonded to themselves as a gas? O2, N2, Br2, Cl2, I2, F2. Okay? So those ones, we're always going to have an oxidation number of 0. But if you use the rules we talked about at the beginning of class, you don't need to remember those. You can just say it's bonded to itself. That means that you have to split those electrons evenly because there's no more electronegative element. All right, so now we have all the oxidation numbers. I want you to talk to your neighbor, identify which one gains electrons and what loses electrons. Actually, I think I have that as a clicker question. Let's try this. I have no idea what this looks like on my end, but... Can you only do one click?
Yeah, you can only do one.
Okay, then talk to your neighbor and alternate which ones you do. Don't do the same one as your neighbor. Maybe the back half of the class, you work on the products. The front half of the class, you work on the reactants. Front half of the class, click on a reactant that changes oxidation number. Back half of the class, click on the products that have changed oxidation number from the reactants. All right, a couple more seconds to click on the screen. Very curious to see what this looks like. Has everyone clicked? Thought we had more than this. Yeah, you have to hit the send at the bottom. You click on it and then you hit send. Is that right?
There it is.
All right, 48. Sweet. It's interestingly small. Okay, we can get the gist of it. So the gist of it is, I'm hoping that there's only one click there. Why is that click maybe not the best place to click? Josh?
It doesn't change.
What doesn't? Yes.
It doesn't change on the product side and the reactant side. It stays the same. It's a spectator.
Between the two sides, yeah. So sulfate is the same before and after, so there is no change in oxidation numbers or the sulfur or oxygen in that. It stays intact as a sulfate. So the only change I would make to this is it's a bad color, I would disagree with that one click. And it looks like a couple people did that on the product side as well. So if we go back and we take a look at the changes in oxidation number. So aluminum goes from 0 to a +3. What is it that changes the opposite way? So wait, is that aluminum gaining or losing electrons in the process? Talk to your neighbor. Is it gaining or losing electrons in the process? All right, we're going to do old school hand raise. Is aluminum gaining electrons left to right? Is aluminum losing electrons left to right? Okay. What do we call that?
Oh, I've heard of that. I know exactly what he's going to say.
Leo the line goes grr. Oil rig is another way to remember it, right? Having some way to remember which is oxidation and reduction is really valuable, especially if you don't do it all the time. So make sure whichever one you choose, you remember. Leo goes grr. Right? Losing electrons, oxidation. Gaining electrons is reduction. That's just the terminology that we use to make it quicker than saying that is gaining electrons. You can say that's oxidized. But gaining electrons, no. Reduction. I have to look at my things too. Right? So we just say it's reduced. Right away we know that it's gaining electrons. In this case, that aluminum, is it oxidized or reduced? And then let's take a look at the other one that changed the oxidation numbers. The hydrogen went from a +1 to a 0. Is that oxidized or reduced? And then here's one term that I think you guys got in your homework, the agent. So if something is reduced, it had to have a reducing agent, something that forced it to gain electrons. What forced the hydrogen to gain electrons? This is the reducing agent. It's the one that allowed the reduction to happen. Do we have an oxidizing agent in this reaction? What is it, Tyler? What's the oxidizing agent? The oxidizing agent is reduced. In order for it to gain electrons, it has to force something else to be oxidized. It has to be the agent that makes that process occur. And that thing that's oxidized is the reducing agent. Questions?
Is it always going to be the opposite?
Yep. Because if you think about the agent means something that's allowing that other process to occur, and there's only two options.
So by extension, the reducing agent is the thing that is oxidized.
All right. So I want you to go ahead and to write out the half reaction for aluminum. You guys practiced this before? So you want to do this one together and you guys do the other half reaction by yourselves? So the half reaction for aluminum says we're going to start with aluminum, and that ends up generating Al3+. In this case, we have two of them. We could balance it later before. It's fine. So if this is happening, which, do we say that it's gaining or losing electrons, aluminum?
Well, we're losing.
So if this aluminum solid is losing electrons, then that means they're separate in the product. Is that right?
Would that be 6 because you have 2 aluminum?
Stop. Don't yell it out. Don't yell it out. Let people think. So why is this wrong? Why is 3 electrons wrong? Think about charge. Talk to your neighbor. How does the charge of that result in an unbalanced equation? All right, can I hear from a new voice? What about this equation is unbalanced? Why? How do we know that?
the 3 plus, since there's 2 ALs on the product side, that would be a 6 positive charge. We need 6 electrons to be able to balance out 2 negative charges on the reactant side.
Great, so we look on the left side, there's no formal charge here. There's a plus 6 formal charge. Now we have a 3 negative on that side as well. Both sides have to be the same. It's balanced, right? Just like we balance the number of atoms of each element, we also have to balance the charge on both sides. So if I was to stop this right now, the right side has a plus 3 formal charge, the left side has a 0. That doesn't work. So that means that this reaction, every time it goes with 2 aluminums, it generates 6 electrons. Can you guys do the second half reaction now? Go ahead and write the second half reaction. Is this the oxidation or reduction half reaction? I'm hearing both. Aluminum is losing electrons. Those electrons are lost. They're out here afterwards. That's the oxidation half reaction. Go ahead and write the reduction half reaction. I think you have some space below for that.
You said that the species being oxidated and reduced is opposite of the oxidation reaction. It's like, was hydrogen the one being, the species being oxidized?
Hydrogen is the species being oxidized. It's not sulfuric acid. Good question.
Yeah.
Sulfuric acid, when you put it in water, separates into H+. Sulfate stays intact, reactants to products.
I just felt like hydrogen was in the reducing reaction, but it's the species being oxidized.
Let's go ahead and write it out, and then we'll talk. Wait, it's an eagle, it's not a chicken. All right, 30 more seconds, then I want someone to volunteer to read off their half reaction for the reduction reaction. All right. Can I hear from Evan?
3H2 plus 1, and then it goes to the product of 3H2 plus 3 electrons.
Plus, say again?
3 electrons.
Okay. So there's a couple things I want to tweak about this. When this dissolves, do we end up with hydrogen gas? What do we end up with? We have a sulfate and 2 H plus ions. So how many H plus ions are on the left side of this equation? So let's tweak that. So we have 6 H plus ions. And they're generating 3 hydrogen molecules. So do we put electrons on the right side or the left side? Let's look at our formal charges. On the left side, we have plus 6. On the right side, we have minus 3. So what can we do to arrange this, Ruby?
You can do the 6H plus and then add 6 electrons on the left.
So we're going to say that those 6 H pluses, everyone is going to gain 1 electron, because over here we know their oxidation number is 0, and they have a plus 1 on the left side. So now if we look at the formal charges on the left side, or oxidation number, either one we want to look at, we have plus 6 and minus 6 on the left side. We have 0 on the right side. If we're talking about a reduction reaction, where are we always going to find the electrons? Are they reactants or products? They're always going to be reactants, because whatever we're reacting accepts those electrons. They're combining, they're being gained by our reactant. And then if we want to take this all the way home, Here's our two half reactions. What happens if we add those two reactions together? What do we end up with on the left side? Go ahead and do that. Add up your two half reactions. What do you have on the left side of the reaction? What do you have on the right side? Cancel out anything. There's spectators that are on both sides. Not spectators is the right word. But anything that ends up on both sides that's identical, you can remove that. And looking at the clock, this is maybe one that we should work through together real quick. So what's on the left side? 6H plus aqueous, 6 electrons. Left side, 2Al, 3 pluses. We have a balanced equation. We could have done that before, looking at our two half reactions, saying, well, if one is giving up 6 electrons, the other has to accept 6 electrons. This is a transaction. We're saying that if someone is taking electrons, they have to come from somewhere. Where are they coming from? They're coming from the other half reaction. So this, we cannot have a redox. The reason we talk about an acid-base reaction the same way. You can't have an electron transferred if it doesn't have somewhere it's coming from and going to. This reaction, the top two reactions show that one of them is giving up electrons. Those are the same electrons as these. The reaction can't happen unless you have the same number donated as accepted. Josh?
What happens if you don't have, they're not balanced, the half reactions aren't balanced?
Then you multiply them by a factor to say how many times. So if we did this without a balanced equation, we would find that top reaction would be Al goes to Al and 3 electrons. We know that needs to happen 2 times to generate the 6 electrons needed for the second reaction. So we have to find some way that there's an even multiplier. Good question. All right. So we have 2 minutes left of class. You guys have some practice problems there. I'm going to do one thing, kind of set you up for your homework that you have for Friday. This animation is so cool. This is literally the live wind currents on Earth. So you can take this, you can move it around, you can zoom in on a certain place, you can go in here, and you can change. Well, I don't want it as now. I want it as a few days ago. So you can change when it is, the actual date, and you can look at so I looked at, for instance, when there was a hurricane. You can go back and see what the wind currents were. So what we're going to be doing next in our class is we're going to be talking about gas laws, and we're going to be talking about how it is that we start to envision gas laws as more than a section of, hey, I still have a few seconds left. Everyone packs up and gets super loud. We're going to stop thinking about it as a set of equations. Gas laws can be some of the most fun and interesting parts of the class because we get to talk about weather patterns, we get to talk about breathing, a number of different things. And so what I want us thinking about, the last thing I want to leave you with, pressure is a really intangible concept, right? What does pressure mean? Something higher or lower pressure. What I want us thinking about is that pressure is, if you look at the side of a container, whatever we're measuring, we have these things that have mass. They hit here, they have a certain force. Depending if they're heavier and they hit at the same speed, they're going to have more force, divided by the total area. So I want you thinking about what happens to gas particles that are always moving around, that have mass. If you have a heavier xenon versus a lighter helium, what's going to happen to the mass and the force that hits the side of that? We're going to spend a lot of time working on that on Friday. You're going to do a little bit of math before class, and then we're going to do a really conceptual in class on Friday talking about sea breezes and that kind of stuff. Happy Halloween, guys. What's your costume?
Oh, dang. Tell that to the other Josh. I'll go tell him.
What's that?
I don't know your last name.
Milner.
Okay. I only have Henrik numbers. Yeah, he's got you.
So sorry.
Amber? Yep. Here, I can take them.
I think Steven's on top.
What?
I'm not quite clear your question. So if something is being oxidized, it is reducing.
Ashley, later. I was hoping to be the one on top, but it wasn't. There you are.
It is being oxidized.
Maggie! Aaron, can I? Sorry, I'm so slow.
Because in order for something to be reduced, something else has to give up an electron. So it allows the reduction.
Maggie, I thought you were here. Maggie. Hey, Dr. B. How are you?
Mark, you're all spiffy today.
Mohammed?
Yep.
I know you're here. There you go. You're
My class is
welcome.
repping hard today.
Yeah, we are.
Oh my god.
Sugar mama.
I welcome.
Fair enough. Hey, you know what's fair crap? I had a inflatable gorilla costume, but I forgot to bring the batteries to it. So
Oh.
it's gonna be a banana instead of a gorilla.
It's an interesting take, though, to be the banana and carry the gorilla.
Yeah, exactly.
I mean, it's
Oh my god.
Turn the tables on the gorilla.
got some Gryffindor right back there.
That's right.
Did you ask him to dress up?
Yeah, I'm giving bonus points.
Good guess.
All right, Iron Chef.